We're now going to look at the torque and angular momentum of a satellite. And the first thing we need to know about satellites relative to calculations is that we will always be considering the satellite to be a point particle. Now, our first consideration, torque here, we can see very quickly leaves the conversation because there is no torque generated by the gravitational force as a satellite remains in stable orbit. Remember that we are using our definition for torque always, R cross F, to calculate the torque on an object. If we are considering, as we are, the pivot point to be the center of mass of the Earth, then our R vector goes from the pivot point out to where the force acts, and the force is acting on our point particle satellite. When we take R cross F, we draw the vectors from a common origin. So I'm going to slide the R vector out here and draw the R vector, and the F vector, our gravitational radially inward force from a common origin, and we can see we get our 180 degrees right here. So that is our sine of 180 degrees in the cross product, and we get no torque. Well, a consequence of no torque is that we get no angular acceleration because there is no oomph causing the satellite to increase or decrease its angular speed. So we have zero angular acceleration. So please box this equation over here. Zero angular acceleration then gives us the consequence that the angular velocity is constant, and since acceleration is time rate of change of velocity, that is a natural outcome of no angular acceleration. Well, how about angular momentum? The angular momentum of a satellite is given by L equals I omega, right? The angular momentum of a satellite of any object is I omega. Now, since the satellite is a point particle, we're going to start with our R cross P down here in a moment. But even before we calculate the angular momentum, since torque equals I alpha, and we know torque is zero, and Newton's second law in momentum form is torque equals dl dt, time rate of change of the angular momentum. L, therefore, must be a constant. So since the time rate of change of the angular momentum is zero, L is constant. L equals I omega. It's a point particle, mr squared. So we get mr squared omega. And we confirm that when we do R cross P, because when we do R cross P, let's get that in here, P is mv. So here now we have sine of 90 degrees between the R and the mv. So let's just go back and confirm that that is understood. The v vector is here, tangent, right? So we have 90 degrees between R and mv. So we get R mv, v equals omega r, so we get mr squared omega. So the torque and angular momentum is not very complicated mathematically, often appears as multiple choice or concept type of question, where we need to know that the torque is zero, the angular acceleration is zero, the angular velocity is constant. If the angular velocity is constant, the angular momentum is constant, and the angular momentum for a point particle satellite is mr squared omega. So while it is all important to know for the multiple choice concepts questions, beyond that, it is not used very much. Well, the last thing we are going to look at in this short lesson is changing orbits from a smaller orbit to a larger orbit, or from a larger orbit to a smaller orbit. Now, we know the equation for a satellite in stable orbit is given by the circular motion equation, where we have the radially inward force is a circular motion radially inward. mv squared on r is given by the gravitational g, mass of Earth, mass of satellite, divided by r squared. The m's for the satellite cancel out. We lose one of the r's, and we get our standard v equals root capital G, mass of the Earth, divided by r, where r, of course, is the radius of the Earth plus the h, the altitude that the satellite is at. So we see that in terms of asking ourselves which satellite is moving fastest, if we look at this equation, we immediately see that as r is smaller, v is bigger. So if you want to put a satellite into orbit at a very low orbit, that is the fastest that the satellite is going to have to move. At higher orbits, the speed of the satellite is going to be slower because of the r in our equation for the stable orbit satellite. So we have a little bit of a consideration here for changing orbits. If we're going from a larger orbit, A, to a lower orbit, B, we first have to slow down. So we have to get this thing out of orbit. We have to get it coming down. So we have to get it coming down. So it's going to kind of spiral down here, spiral down, spiral down, spiral down. When it gets to the orbit that we want it to be in, we need to turn those thrusters on and have it achieve the higher speed v that it needs to then go into stable orbit B. Now, in going from B to A, of course, it's the exact opposite. We're going to need to speed up to get the satellite to get up to the higher orbit. And once it gets up to this higher orbit, to keep it in a stable circular motion at that point, we're going to have to reverse thrusters to slow it down and keep it in our stable circular motion orbit at that point. Now, there is one more aspect to changing orbits and changing speeds while in orbit that I would like you to make sure you have into your notes, and that is the last little bit down here, where we are stating that if you increase the speed a little bit from a lower orbit, you will, and that's all you do. So it's not about speeding up and then slowing down, you just increase it. You will not escape the gravity of the Earth, but you will fall into a stable elliptical orbit. To continue to leave the gravity of the Earth, to spiral away from the Earth, you would have to achieve what is referred to as escape velocity. We will talk more about that in another lesson. But I do want you to know, again, for a multiple choice type concept question, that if you increase the speed of a satellite, and that's all you do, you will go into a stable elliptical orbit. If you decrease the speed of a satellite, and that's all you do, you will spiral downward, the satellite motion will degrade and eventually collapse into the Earth. So, here you have your annotations for changing orbits. Please make sure you have everything copied down, and we will continue on.